Welcome, I hope you're well. I'm Dr. D. Today we are going to continue talking about dispersion. In the last video I covered two measures of dispersion, relatively simple measures, range and IQR. And dispersion, just to refresh your memory, is the spread outness of our data, right? It's how spread out it is. Again, spread outness, not a word. That's all right. You get the idea. So, if our data was all the same, right, in one point, right, it wouldn't be interesting. Every article of clothing would be exactly the same size. You only ever have to make one color of anything. But in practice, in real life, fortunately, there's variation, right? Variety is the spice of life, as we say. Well, it certainly is what makes statistics interesting and useful, right? Is how spread out our data are. And so what we're going to talk today about is other measures of dispersion beyond range and IQR, or interquartile range, that capture the dispersion in our entire data set. So what we're going to look at first is a measure called sample variance. Sample variance is one of the most important measures of dispersion, and it has a formula that's going to look a little bit complicated, just to give you a heads up. We're going to take it apart, so when you see it, don't just pause and close your browser or anything. We'll take it apart, you'll understand this by the time we walk through it, but here's the formula. So our symbol for sample variance is going to be s squared, so that's a 2 up there. And s squared is equal to the sum, a big sigma means the sum, from I equals 1 to n of the quantity xi minus x bar, the quantity squared, all divided by n minus 1. Okay, so let's take that apart piece by piece. Well, we just said that s squared is going to be our sample variance. So we know what that means, right? What other symbols do we have in here? Well, we have this fraction bar, which is going to be division, and I mentioned in another video, but I'll mention it again. The division symbol is just a fraction bar with a little something on top and a little something on bottom. So a fraction bar is what we use to divide. So under the fraction bar we have n, and n is our sample size. That is how many observations we have. It's cross-sectional data. It's also how many elements we have. With time series data, it's the number of times that we've taken a measurement for the particular element we're observing. But whatever we do on top, and that's the messy part, we're just going to divide it by n minus 1. So that part should be understandable. Now what's on top? Well, the big sigma over here, I'm going to put it over here. This is our summation symbol. And it's an operator. Right? It's an operator. It's a big sigma. It's a Greek letter. And it's an operator. You know what operators are because I just drew one up there. That's an operator. Another operator is this. Another operator is this. Another operator is this. Right? Whatever the multiplication sign. Or maybe you just write it like that. These are all operators. And operators take numbers and do stuff to them. This summation symbol takes numbers and sums them, right? But unlike these numbers, which are all binary operators, which take two numbers, this can take any number of numbers and sum them, right? And so this is, it'll add up a bunch of numbers. It has a superscript and a subscript. The subscript, I equals 1, tells us where to start. We start with the first number, a number, the value to the right of this that has an index, a tag on it that says 1. And we're going to add up until we get to the superscript, which is n. So we're going to, whatever the stuff is that's over here, we're going to start with the first one, and then add that to the second one, to the third one, to the fourth one, to the fifth one, to the sixth one, and so on until we add up all the way till we get to our sample size. That is the end. That's when we're done, right? What are we going to add up? Well, this formula tells us that what we are going to add up is the squared difference between xi and x bar. So what is xi? Well, xi is x, value of x for observation I. What is x? Well, that depends. We're going to have to assign something to x. And then we're going to give each observation an index, right? So each person if we're measuring people, or each unit if we're measuring products. And so let's just say up here maybe, let's let x equal height. We'll be measuring height, variation, dispersion in heights. For historical reasons, statistics started by studying French soldiers' heights, so we're going to continue that tradition. And then x bar, I cover in a previous video, x bar is the sample mean value of x. Now, we had a similar formula to calculate x bar. The formula for x bar is the sum from I equals 1 to n of x sub I over n, which you know more or less formally, but more popularly as take all the numbers and add them up and then divide by how many there are. Well, that's kind of what we're doing here, right? But instead of taking all the numbers, we're going to take all the squared deviations from the mean. Right? Before, we would just take all the heights. But here we're going to take all the squared deviations from, not of, from the mean, add those up, and then divide by n minus 1, by however many they are, minus 1. So let's do that, okay? Let's follow this formula. What we're going to do is we're going to start, and then for each observation, we're going to calculate the difference between the mean and the observation, xi minus x bar. We're going to take that difference and square it, and then we're going to add those up, and then we're going to divide by 1 less than the number that we have. So in order to do this, here, I'll rewrite the formula over here. I have some data here that some pretend people that I'm going to pretend that we measured their heights. So s squared equals this sum xi minus x bar squared over n minus 1. Bingo. There we go. So here are my x's. And now I need to find x bar. Well, I did this already, but we're going to add them up. 6 and 4 is 10, 3 and 7 is 20, 0 carry the 2. Add these up, you get 32. And we have to divide by however many there are. 320 divided by 5 equals 64. Okay. Oops daisy. Back down we go. Okay. So 64 is my x bar. I'll put that over here so I can refer to it later if I need it. Now what I want to do is I want to create another column called xi minus x bar. And now I want to subtract 64 from each of these, right? So 66 minus 64, that gives me positive 2. 64 minus 64 is 0. 73 minus 64 is 9. 60 minus 64 is negative 4. And 57 minus 64 is negative 7. Now we've got to be careful. We have to square them before we add them. If we add these up, we'd get 0. We always would get 0 because on average, the deviation from the average is 0. That's why we call it the average. So we want to be very careful. Do not add yet. We have to square it first. Squaring it has two effects. One is it prevents these negative numbers from offsetting the positive numbers, right? Because when we square these negatives, they're all going to be positive, and so the deviation is going to get additive. We could do that with absolute value, though. We don't do it with absolute value generally, partly because squaring it over or adds additional weight to outliers, which you can argue that we have more dispersion if we have more outliers. And another one is that it has nice theoretical properties. It does some nice things for us if we play with it a little bit. It shows up a lot later on in formulas and theorems. Okay, so let's square these. Let's pick a brighter color. 2 squared is 4. 0 squared is 0. 9 squared is 81. Negative 4 squared is 16. Positive 16, right? And negative 7 squared is 49. So let's add these up. 4 and 1 is 5, and 6 is 11, and 9 is 20. 0 carry the 2. 2 plus 8 is 10, plus 1 plus 4 is 15, so we have 150. So we can rewrite this if we want as the sum from I equals 1 to n of xi minus x bar, that quantity squared. Well, that's just this right here. This whole thing turns into 150. Right? So that's the numerator. Now in order to find s squared, we need to divide that, right? We have 150 divided by n minus 1. So what's n? We used it once already. N is 5. So s squared is going to be 150 divided by 5 minus 1, or 150 over 4, which is going to be 75 over 2, which is 37.5. Cool. Now this should always be positive. You can see that because this is always going to be positive, and these should all be positive, and so s squared should always be greater than or equal to 0. It would be equal to 0 if everybody was exactly the same height, right? Because if everybody was exactly the same height, they would all be equal to the average, and then this would be 0. And so the distance from 0 is a measure of the variation. Okay, so what the sample variance is useful. It's useful for a lot of reasons, mostly useful because it captures all the data, it uses all the data, and takes advantage of that. But it has one disadvantage, one big disadvantage, which is when we square it, we went from x in inches to something like inches squared. And with double digits, that's not a big deal, or variation that's in a single units, that's not a big deal. But if you're starting to talk about tens of thousands of dollars or something like that, you can get very large variances. In addition, you can't really compare it to X bar. And so the more important measure of dispersion, slightly more important, is the sample standard deviation. In my opinion, I don't know, people might disagree about whether it's important. Certainly later on when you talk about theory, you get into variance covariance matrices, and the variance comes up a lot more often. But here we go, sample standard deviation. We're going to define that with the letter S, and the formula here is really straightforward. It's the square root of S squared. Now, S squared is always positive, so S is always going to be positive. Sometimes this is written as S sub X because it's a sample standard deviation of X. But if we only have one variable, usually we suppress the index. And if you want to get directly to it without going through the variance, you can just rewrite the S formula in here. The sum of xi minus x bar squared over n minus 1. Right? And so that works. That'll get us where we want to go. That's a sample standard deviation, and that's pretty handy. So let's calculate it in this case. If S squared is 37.5, then S is going to be the square root of 37.5, which is 6.124. I calculated it in advance. You can tell just by looking it's going to be 6-ish, right? Because 36 is 6 squared, but 0.124 is the stuff you got lying around. Okay, so those are the sample variance and the sample standard deviation. These formulas will get you that every time, and they're really useful. One way that they're useful is that they're good predictors of the population variance and the population standard deviation. So these are what we generally really care about, because we don't just want to know the variance of 5 people's heights, we want to know the variance of height in general. The problem with the population variance is that we can't actually find it. But what is it that we are looking for and shooting for? So the symbol for this is a little lowercase sigma. It's this right here. It's like a little circle with a hat, something like that. And it is going to be the sum from I equals 1 to big N of x sub I minus mu, the quantity squared, over big N. Big N we can't actually count. It's very hard to count. And sigma, or mu we can't actually find. But if we could, and in rare cases you can when you have a simulated population or something, so you know everybody who's in there, then that's useful. That's sigma squared is what we usually call this, sigma squared. And then similarly we have sigma equals the square root of sigma squared is our population standard deviation. And so those are what we're usually shooting for. Okay, finally, in addition to variance and standard deviation, once we have those, we can calculate what is called a coefficient of variation. Now this is convenient because the coefficient of variation is unit independent, right? So the problem with our variance is that it was unit squared. Our standard deviation still has the units that we started with. Coefficient of variation gets rid of units entirely, so we can compare totally unrelated data sets. And usually we write the C sub V, and this is going to be our standard deviation divided by our sample mean. Sample standard deviation divided by our sample mean. You can do this for the population too, in principle. And so here we had 6.124 divided by our mean, which was 64, which is going to be 9%. 9%, I think. I don't have my calculator open. Calc. There you go. 6.124 divided by 64. Yeah. 9.57%. 0.957. Or 0.0957. So that tells us just that the standard deviation is 1/10, a little less than 1/10 of our sample mean. So there you go. Those are measures of dispersion, variance, and standard deviation, and coefficient of variation. And these all measure dispersion via squared deviations. Later on, much later when we get to forecasting, we'll talk about absolute deviations and absolute values, but in general, these are the ones that we're going to use the most often. So I hope you found that useful. If you have any questions, feel free to post them on comments or email me. I'm Dr. D, and I will see you guys next time. Thanks for hanging out. Bye.